And if you're just joining us now, I'm just currently messing around with this space here and kind of demoing a little bit about what we're going to be creating today. We're going to be working on this kind of lightning algorithm to generate this kind of nifty lightning effect. And similar in spirit to yesterday's lesson about creating a fractal machine in some sense, but we're going to be doing it in a slightly different way, in a little bit more straightforward way. And we'll be able to get this kind of really nice realistic lightning effect, which looks really nice. And we can pause it halfway as it's going and take a look at it here, check out the detail of it, and see all the different branches that we're going to work on today. And as always with these type of algorithms, we're going to start with kind of doing it the slow way, and then we'll optimize it so that we can kind of do it in real time like this, and as so often is the case with these kind of algorithms. There we go. Nice detail of this thing. I'm going to give it 30 more seconds, and then we will get started. This will be a fun one. Get roasted here if we stay down here. And we'll even add sound too. If we have a little bit extra time, we'll add the thunder sound too. Right now this doesn't have any sound, but we can add that later. Okay, so I'm going to do File New, and we're going to start from a fresh world here. So with a lot of different things like this, there's really no magic to generating something like lightning, right? I mean, if we take a look at the way nature does it, it kind of seems to follow almost a randomness. So it's not like there's some magical formula to do this. We just the best way to really go about implementing an algorithm like this is just to start with images. So let's take a look at lightning images. It's kind of where you kind of begin on these kind of when we want to develop these kind of looks. And so if we take a look here, you know, we basically want to do something that follows this general principle here, where we have this kind of major array that kind of goes from the sky to the ground, and then you have these tributaries that kind of come off that are always, they appear to be smaller than that main ray. So we have our primary ray, and we have smaller ones, and we can kind of see that the primary ray kind of makes its way to the ground fairly directly. I mean, there are some cases here where it does kind of tributary, kind of goes off to the side, but for the most part, it seems to be pretty vertical. And then it's the little ones that kind of come off and go in crazier angles. And so we're going to kind of use that as our kind of our model here. We're going to basically try to recreate this idea of a root trunk, and then we're going to create these subtrunks that are going to kind of come off and go in slightly more random angles. So that's literally to come up with this. It's just let's take a look at an image and let's see if we can recreate it, basically. And that's kind of how this was developed and how we can go about doing this. So the first thing we're going to do is we're going to first build our lightning primitive. This is essentially the unit segment that we're going to kind of extrude out and then continue along this random pattern. And like we've shown in other demos, we're going to be using a cylinder to do this. So I'm just going to take a cylinder and I'm just going to draw, this is going to be our lightning segment. And the other thing we're going to want to do is we're going to normalize this so it's a little bit easier to work with in script. And so to do this, I'm just going to do a couple of things. First, I'm going to remove its rigid body and this trigger activating attribute. We don't need that. And then in its shape, I want to make sure its height is set to exactly 1, because we're going to be using the transform scale to modify its height. And so if we set the height of its underlying shape to 1, its scale will map 1-to-1 to the actual height of the object. The nice thing about using the transform scale is it's actually much more efficient than setting the shape. The height value, because if we set the height value, it has to go and recompute the mesh data itself. But if we set the transform scale, this is all done in the GPU. The actual like transforming of the vertices is done in the GPU. So if we can animate this value instead of this value, we can gain some extra performance benefits. And then the other thing I'm going to do is, so you'll notice that the origin of this line, this cylinder, is in the center of it, which is mathematically kind of a pain, because as we position these things, we want to kind of do it from the endpoints, not from the center. And so to shift that, I'm just going to create a new vertex transform under a mesh modifier, and I'm going to just set the position. I'm just going to offset this by -0.5 on the y-axis. So that means since our lightning is going to go kind of downwards, it means wherever we position this in world space, it's actually the top point of it. And then all we have to do as we make copies is essentially place these kind of at the bottom. Essentially, this is what we're going to be doing right now. I'm going to just kind of like do this manually here, and then we'll write an algorithm to do this. It's going to essentially take this initial one, and it's going to make a copy of this. It's going to set a random angle about that, make a copy of this, we'll set the endpoint to that last position, choose a random angle for that, and so forth. So that's the algorithm that we're going to write. So now we have our line primitive here. One other thing we can kind of do is we can go edit its material, and we'll make it illuminate kind of brightly. So I'm just going to click on its material. We're going to just use the default material. Should be fine here. And then I'm going to set its illumination emissive amount. I'll just set it to a value that's pretty large here. I'll just set it to 380. So you can start to see it starts to glow. And this becomes much more apparent if I go to nighttime here. It really glows. In fact, we'll knock it down a little bit. I'm going to set the emissive amount to maybe set it to 90. That's pretty good. So we now have our lightning unit. This is what we're going to be extruding along our direction of our lightning bolt. The other thing I'm going to do is I'm going to just create an empty node under entities. I'm going to go to node. I'm just going to put a blank node in the space. And this is something we're going to be using. We're going to make copies of this, and we're going to stick all of our lightning bolts on these nodes. And then we'll package them all inside this node, and that'll make things nice when we're calculating local randomness with respect to the trunk's a branch's angle. And this will become clear when we start working on this algorithm. So we have our two things that we're going to need for this. So the next thing we're going to do is we're going to start to build our actual script to perform the lightning. So to do that, I'm just going to go inside the browser, click on terrain space, and I'm going to right click in here. I'm going to create a new global script. So this is going to be, I'm going to give this a name. This is going to be our lightning manager. Think of this as our central location where we'll expose a function that will basically generate a lightning bolt from a particular location in space. We'll be able to do that through this object here. And now I'm going to edit this thing's script. So when we do, anytime we create a new global script, it creates this little like demo, this little example script. I'm just going to delete this out. And we're going to actually now implement our draw branch function. So this is going to be the function we're going to call to create a lightning branch. And because this is going to be a kind of, well, we'll start doing it this way, and then we'll be modifying kind of how we call this function in a bit. So what draw branch is going to take in is it's going to take in a position in world space. Right, well, actually, we're going to just call it position. You'll see why. This is going to become a local position in a second, but for now, it'll just take in a position. So any position in space, we're going to give this function this position, and then it's going to draw a bolt from that. So let's work on the root trunk. Let's work on this first part here. Before we worry about all the complexity of all these sub ones and stuff, it's just nice and easy to just think about starting simple with this bolt here. So you kind of saw as I was drawing, essentially, I started at some position in the sky, and I made a copy of that, and then I kind of chose a random angle, and then I made a copy of that, and I chose a random angle. And that's basically what we're going to do to generate this root trunk. So we're essentially going to enter a for statement, and we're going to step through. But actually, a better way to do this is we're also going to specify a maximum length. So there's lots of different ways we can go about this, but let's also, as a second parameter, specify the length of our bolt, or of our branch. So it's going to take in a position in space, somewhere up in the sky, and then the length. How far do we want that bolt to travel? So now we have everything we need to kind of build this bolt. So the first thing we're going to do is we're going to make a copy of this node. And the reason for that is we're going to stick all of our bolts, all of those like segments, we're going to stick them inside this node, this copy. In fact, we're going to call that copy a branch. Going to clone as a shared copy. So we're going to just literally just take this node object here, we're going to make a copy of it, and then we're going to stick all of our copies of our bolt inside that copy. So we have a nice packaged object. We'll keep all of our stuff inside there. And now we're going to basically repeat until we reach the end of our bolt. So basically we're going to maintain the length, the total length that we're moving down this bolt, and once that goes past our max length, we're going to exit out of this loop. So we're going to initialize length to 0. And so every single time we're going to step in and we're going to add a bolt. We're going to add up the length of that sub bolt. And once that goes past our maximum length, we've created our full bolt, our full trunk. So the other thing we want to be aware of, and we'll do this now, is we want to define all these variables as local. And the reason why is we're going to be recursively calling this function when we draw those sub branches. So eventually we're going to we're going to update this function to also handle all these sub-branches, which is just going to be a recursive call of this function. And so whenever we're dealing with recursion, we want to make sure we declare our variables as local. That means every time we call the function, there's a local copy of that state. And then when we come out of the recursion and we're back in the parent call of that, it will also have its own local values. If we were to declare a variable that wasn't local, like d, let's say 0, and then we were to call this function again, let's say we call it draw branch, and then it re-enters here, let's say we modify d. When it comes out of this draw branch function and it continues on from the previous draw branch function, d will have been mutated by this function call, by the recursive function call. But if we make them local, then they each will preserve their state in their local calling context. So long story short, just make sure, in this case, we declare all of our variables as local. So the first thing we're going to do is we're going to make a copy of our cylinder. And I'm going to actually call this our bolt. We'll call that, actually it's not really a bolt, it's like our segment, our lightning segment. So I'm going to drag and drop this in here. This is our kind of root one. We don't want to modify our source one. We just want to make a copy of it. So I'm going to say clone as a shared copy. And that's going to be stored in a variable I'm going to call line. And the next thing we want to do is we want to parent this line. We want to set its parent node, set parent node to our branch. This is the node that we created when we entered this thing. And the next thing we want to do is we want to start positioning it and choosing a random angle. So the position is something we're going to be kind of, as we're looping over in this loop, we're going to want to kind of continually update a position. So we're going to define a vector 3. This is our v npos. Actually, sorry, that's not vector 3. We're just going to initialize it as 0, 0, 0. So by the way, this is all going to be done in local coordinates. So because we're adding this to a node, 0, 0, 0 on that node, wherever that node happens to be, will be relative to that position in its parent frame. So we're going to do this all in local space. This is going to be important because once we start creating our sub-branches, by working in local space, it makes the math much easier. So our start position initially is 0, 0, 0. So the first thing we're going to set this line, its local position. We're going to set it to that. And then we're going to advance our end position by our length. So the other thing we're going to do is set the length of our line. So we're going to just choose a random value. We're going to say math.random. This is our line length. So length is equal to math.random. Now when we call math.random without any parameters here, it returns a value from 0 to 1, a random number from 0 to 1, which is perfect. If we take a random value from 0 to 1 and we multiply it by 5, for instance, we're going to get a random value from 0 to 5. So that's perfect. We want our bolt to have some random length that's 0 to 5. And actually what I'm going to do is I'm going to say 0 to 5 plus 1. That means it'll have a minimum size of 1. Because if math.random returns 0, for instance, then this goes to 0, and the minimum will be 1. But if it returns 1, this will go to 5, and then this will go to 6. So essentially what we've done here is we're now choosing a random length that's 0, that's going to go from 1 to 6. Actually, I'm going to do 1 to 5 instead. So we're going to set now our length's local scale, and it's going to be a vector 3, and it's going to be, we're setting the y value of this. So we're going to set the y value to length. So notice that when I go into the cylinder shape and I set the transform and we set the y value, you'll see that it grows in that direction there, in the vertical direction. So this is going to be placed in the node, and then we're going to choose a random y value for this. Oops, a random y scale here. So it'll either be as little as 1 or as great as 5. And what else? Oh, so the next thing we want to do is choose a rotation for it. So if we look here, we can kind of see that, I don't know, they don't seem to go more than maybe 40, 45 degrees. I mean, there are some examples where they go 90 degrees. I mean, lightning can certainly go in any direction. There's no rhyme or reason. But overall, it seems like it kind of maintains this. The branches never seem to deviate more than 45 degrees. But they can go horizontally. Certainly, if you just keep going 45 degrees, it will eventually circle around potentially. So I think overall, each individual segment doesn't seem to go more than 40 or 45 degrees off the previous segment. So we'll choose that as a value for a random angle. So how do we choose a random angle? Well, first thing we're going to do is we're going to declare a couple of variables here. Our max angle. This is going to be our maximum branch angle, let's say. our maximum branch angle. Actually, we'll say this is our maximum trunk angle. This is because we're going to have a separate one for our branches. Trunk angle. So we're going to say it's 45 degrees, and for the purposes, and I'm going to explain this in a second, we're going to want half of that. We're going to do our half max trunk angle is equal to our max trunk angle times 0.5. And you'll see why, because what we're going to now do is we're going to choose an angle. So our total range is going to be 45 degrees. So we're going to do a 45 degree. You can imagine from 0, we can go half that in one direction or half in the other direction. So we can kind of, we can basically, if we're going to make this 90, for instance, that we would go negative 45 on one side and negative 45 on the other side. Maybe actually that would look better. Maybe we'll do that instead. Because when I was messing around with this before, I found that 45 was good, but maybe that would look better. I don't know. Let's actually do that instead. So we'll choose 90 degrees as our full range. You can imagine our 90 degrees are full range. So that means on any one side, it'll go up to 45 degrees on one side or the other side. So we're going to now set the lines, set the local rotation. It's a vector 3 that it expects, and it's going to expect a random value. And we're going to multiply this by our maximum trunk angle. So we want a random value between 0 and 90. But then we want to subtract out our half trunk angle. So we're basically for the x rotation. So we can imagine here on here, if we were to take this and rotate along the x-axis, let's see if we can take a look here. We're going to choose from negative 45 to positive 45. So negative 45 to positive 45, like that. So 0 is there. That's why we had to subtract half, because we want to go from negative to positive 45. So that's why we subtract half. So we choose a value from 0 to 90, and we subtract out 45 from it. So it's going to go negative 45 to positive 45. We don't want any rotation along the y-axis. That doesn't make sense. If we take a look at what happens when I spin it along the y-axis, you'll notice that nothing really happens visually there, so we don't care about the y-axis. And then we'll want another random in the same range for our z-axis. And I'm missing a parenthesis here. Nope, too many parentheses. Okay, so vector 3, does that make sense? No, that doesn't make sense. Let's see here. Well, let's just do ang x is equal to, let's pull this stuff out because it's hard to read here. Equal to that. And our ang z is equal to that. So this is going to be your ang y, or ang x, sorry. It's going to be ang z. Close that parentheses. Okay, that's better. Let's and so we're ang x and ang z, and the other thing is this is actually calculating them in degrees. So again, just it's easier sometimes to think of degrees here, so 90 degrees, 45 degrees, and so forth. But our set local rotation function expects this to be in radians, so we just need to convert this to radians. So that is just math.rad. Math.rad is equal to that. So now we should be, every single time we have a segment, we're going to create a copy of it. We're going to set it. So initially, we're going to be setting at the first position, which is 0, 0, 0 of our parent node. We're going to choose we're going to set its position to be there initially, so it's 0, 0, 0. Then we're going to choose a random length for it between 1 and 5. We're going to set the scale of it. That will control the length in this case. We're going to then choose a random angle for it along the x and z axis, and we're going to set that to it. So before we repeat and go to the next one, we want to accumulate our length value. So length is equal to length plus our local length here. So actually, I'm going to have to rename this. So this is our local length. We're going to say this is our branch length. So that because we already used the word length here, so we want to make sure that we don't step on that variable. So that will eventually get us out. So once we keep adding these things, we're going to summate up the length, and that'll eventually get us to exit this loop. So once we've reached that maximum length, we exit out. And the other thing we need to do is update the v_npos so that the next loop will then position the next object at the bottom of the last one, and then continue on that way. So our npos is just going to equal to the current position of our current line here, so the current npos. And then we're going to subtract the local transform, get the up direction. So that's the up direction of the cylinders. That's the vertical up direction. I'm going to subtract this. It's going to the down direction, and we're going to multiply that by the length. So you can imagine that the npos now is just going to equal to the position that we used the previous one, which initially 0, 0, 0, minus the up direction, so that this direction that's facing up, but it's going to be, since it's minus, it's going to be facing down, minus that direction times the length of that. So that should give us a point that's right at the end of the previous segment. And so we've updated the end pos of that, so when we loop around here again, we're going to now make a new copy of the next one. We're going to position that, we're going to set its parent to this branch node that we created initially. We're going to position it at the last position that we calculated there, and we're going to set a random length. And then we're going to continue on, random rotation for it, create a new, and then summate up the length, and eventually we'll exit out when we reach the maximum length. So that should do it. So now we should be able to draw a branch. So let's invoke this function. And so the easiest way to do this is I'm just going to create an on-init function. So I'm just going to hit function. This is going to get called when we hit play, global script on-init. So on-init, we're going to invoke this draw branch function. And let's position it wherever the node happens to be. So I'm just going to stick this up in the sky so that it'll always come out of that location there. So I'm just going to drag and drop this node in here. And I'm just going to say self::draw branch at our nodes get world position. And our maximum length, let's just use the distance between the node and the ground. So it's just going to be its world position dot y. So essentially we're just saying, now that's not, that length, obviously if it deviates a lot away from, there's a lot of random angles, that length will be a little bit short. It won't necessarily touch the ground, but we can eventually modify that to make that a little bit better so it always hits the ground. So now when we hit play, it will draw a branch at the current position of that. It's going to add, and then using the logic here, it should hopefully repeat until it goes. Let's see if this works. And there we go. So this created a couple of segments, not much. I'm going to move this way up into the sky, this node here. And there we go. We got a nice zigzaggedy thing every time we hit play. I don't really like the 90-degree thing for whatever reason. I feel like maybe we can choose smaller segments. That's not too bad. So not too bad. What I'm also going to do is I'm going to crank up the radius of our cylinder shape a little bit, make it a little fatter. So our trunk now has some nice fatness to it. And maybe a little less than that. Like that. So it's pretty good. It's nice and zigzaggedy. It's kind of what we want here. I'm going to adjust this max trunk angle. Let's set it to 50. Less angle. Now it's a little bit more direct. And I think from when I was playing with it before, I found that 50 was a nicer, kind of created a nicer angle. So now we have a nice bolt that hits the ground. And no matter how high we put this up now, it will always kind of reach that ground. So that looks pretty good. So the next thing we need to do, looking at our pictures, we want to start working on these tributaries, these kind of other parts. And by the way, we can keep tweaking this. We can choose, random from 3. So the shorter we make each length, the more we're going to be putting of these things in the space. So the more chances for variance and more detail on the kind of the path that it goes. So maybe we'll leave it at that actually. Okay, so let's work on the tributaries. So for the tributaries, we're really we're all set to go. We just need to basically recursively call this function. We're going to pick a random, as we're kind of making our way down the trunk, we'll randomly decide occasionally to create a recursive call on this function. And when we do, it's going to go and create a new branch. And then we're going to have a little bit of logic here to kind of scale it and choose a random angle for that branch, and then the rest will proceed as normal. So what we're going to do in here is I'm going to it'll be in here. So before we calculate the new end position, because we'll want to kind of pick a random position before we reach that position. So in here, I'm going to the first thing we're going to do is let's choose at a random time. So what I'm going to do is say math.random, and so math.random returns a random value between 0 and 1. So you can think of that as that's 0 to 100%. And if I just am interested in sampling it and entering this logic here when it's less than 0.2, we're essentially saying 20% of the time because it's going to 20% of the time we assume if it's a relatively uniform random distribution, it should give us values that are less than 0.2 20% of the time that we ask for it. So this is a good way to say, okay, 20% of the time, as we're working our way down this kind of branch, we'll decide to create a child branch. And we can adjust this later, maybe make it 0.1, means that it'll be more rare that it will choose a sub-branch. 0.5 will be like very often, it'll create a sub-branch, but 0.2 should be like a pretty good distribution of sub-branches. So the next thing we want to do is calculate because we're going to have to call this function with a position. So we're going to have to calculate a position along that length that we just created, a random position, right? We could choose the endpoint to always create branches at the endpoint, but I think a random position might look a little bit nicer because it'll choose it along the segment, wherever that segment is, it'll choose it along the segment. So let's choose a position for our branch. This is going to be our branch position is equal to, just like we did here, we calculated the npos. We're literally going to take this, just copy this, but instead of choosing a length, we're going to just say math.random times length. So again, math.random is going to return a value from 0 to 1, which will mean since we multiply that by length, it's going to be 0 to length. So it's going to be a value that's going to go from the start of the bolt, from the start of that segment to the end of the segment. Anywhere in between there is going to be our branch position. I'm going to make this local again so that we don't, in this case it won't matter, but I always prefer when we're dealing with recursion. And then we're going to just simply call self : draw branch, and we're going to pass in that branch position. And then we want to choose a maximum length. So each of those, now instead of going to the ground, we're going to just have to choose a length kind of arbitrarily, since it looks like the lightning kind of decides it will eventually end somewhere in the middle of the sky. So we'll just say math.random. We'll say maybe I don't know 20 units as a random length, but we'll also add in a minimum of 10. So it's always, well, actually a minimum of 5. So it'll either go up from 5 units to 25 units. It will be our length. The only other thing we're going to have to do is this will create a branch there, but the branch is going to recall this function, which is then going to create a copy of our initial node, which will have no rotation to it. So all of our branches are going to basically face straight down in this case. Actually, we can probably see what's going to happen here if we hit play. Let's see here. And one other thing that we're going to want to do here. So yeah, we'll take a look and see what happens here. But there's one other thing we need to do, and we need to ensure that this is not going to explode in complexity, because the problem is every time we call this recursively, it may continually, every single time it gets called, and it's starting to work on the child branch, on like a sub-branch, it may keep going into sub-branches and going to sub-branches and going to sub-branches, which is actually what Lightning does. But we need to make sure we kind of eventually exit out, because this could go on forever and it'll get stuck and it'll never exit. So we'll need to build in some sort of short-circuiting system. And a good way to do this whenever you're dealing with recursion functions is you can kind of add a parameter called depth. And when we first call our root function here, we set our depth to 0. And then we just have to make sure every single time we call our function recursively, we just take whatever the depth currently is that gets passed into this function, we add 1 to it. So you can imagine now we can figure out the depth of a recursion just by looking at this variable. So initially it's 0. We're at root 0 when we call this draw branch function. And then every single time we call our recursive function here, we're going to add 1 to it. So then inside here we see that, our depth is 1. And then if we call it again, our depth is 2. And so that's a good way to then say, and our depth is less than 3 or less than 2. So if once we go deeper than 3 levels, this won't get called and we won't go deeper than that. So that's a good way to kind of ensure that it will exit out. Okay, so let's see what happens now. Again, we're not doing any random rotation on those branches, but we are kind of recursively calling this each time. And so we get that, which does not, that looks pretty awful. One other thing we got to make sure here that we're doing. Let me just, again, let's make sure all these things are defined locally. I'm going to actually pull this out, this lightning segment, and put it in here. And again, let's define all these variables as local so our recursion doesn't step on these values here. The important one is length in this case, because that might be what was happening here. Our length, so notice that before we didn't make that local. So when it was calling this recursively, it was coming in here again in the recursive function. It was then setting this. Then when it was coming out, length was now whatever it was inside that recursion function, and that's no good. So we want to make sure we define that locally. Everything else is local. Okay, so let's see if that looks different now. There we go. That looks better, though. But notice that they're all placed at the root node. And so that's one thing we forgot to do here is we also need to set the position of this branch. So when we call draw branch, we're not actually using this B position. So we got to just make sure we set our this branch to that location. So we're going to set its local position to our V position. And so now what's happening is that they all are getting positioned locally with respect to the ground. You can kind of see them off underground here. Let's take a look here. So they're all kind of underground. Let's see if I can move this up here. And the reason why is that we're not reparenting these branches, and so it doesn't look right. Basically, is the long story short. So we have to kind of update our recursion here because we want to basically parent all of our branches to the parent branch that's getting passed in here. And so we just have to update our draw branch function. So this is going to take in our parent branch. So we can then, so as we're creating these child branches, we can then parent them to these child branches. We can then set them as children of this parent branch. And then all the local positions will be correctly relative. Since we're calculating this in the local frame of the parent and we're passing it into here, when we set the local position, it will then be correct in the frame of its parent branch. So long story short, we're going to create the branch, and then we're going to say if we have a parent branch, because we are going to call this the first time, we're not going to have a parent branch. So if we go up here, when we call on init, the first time we don't actually have a parent branch, we're going to pass in nil. So only if we have a parent branch, we're going to take that child branch, and we're going to set its parent node to that parent branch. And then so now it's correctly positioned at the location when we call this recursion function. We're correctly calculating this in that local frame. So let's see what happens when we play now. Branch set parent node nil. Set the parent node. What was the error? Bad argument node expected. Oh right, we got to make sure we pass that in here. So in here we're going to pass in current branch. So draw branch. This is the current branch that we're creating. That becomes the parent of the next of the child branch. And so now they're getting positioned correctly, but you notice that they're all just kind of facing downwards. So we're almost there, we're almost home here. We almost have our thing, but notice that all of the branches are kind of, because it's always just doing everything vertically, it's like choosing, and then they're just simply choosing angles off the vertical, and that's no good. I mean, it looks kind of interesting, but it's not quite what we want. We want the branches to have lots more rotation. We want them to kind of, when they come out, maybe come out at 90 degrees, you know, a lot more exaggerated. So to do that, when we create our child branch, we're just going to rotate this whole branch and give it some random rotation. And then that will ensure that since we're doing everything in local frame, it's like we're creating this root branch, but we're sticking it off like at 90 degrees, and then we're going to calculate everything locally from there, and we'll go from there correctly. And so we're going to just choose a random angle. Just like we do down here, we're going to just calculate a random angle, and then we're going to set that whole branch's rotation to be those random angles that we calculate here. And we might want to actually crank up the trunk. This is why I separated this out into different. I think for branches, they should have a greater range of random angles. Make that 90 instead. So instead here, we're going to choose the max branch angle and the half max branch angle. So again, when we create that child node, we're going to twist it much more at much severe angles. So let's see what that looks like. And there we go. Now we start getting kind of that effect. So we can actually kind of zoom in here to kind of see what's going on since we have all these nodes here. So as we're working our way down our branch, you notice that it reached this point and this random decided, okay, I'm going to create a child node here. And it created this whole child node, but we rotated it now a lot more severely, and then the algorithm proceeded in local space, so it just kind of worked its way down as if it was like completely vertical, and it kind of chose random angles off of that. And so by working in local space, it gave us a very simple frame to work with mathematically. But then by rotating that parent node, we got that whole thing to be basically rotated without having to change kind of our logic in dealing with that separate branch, that child branch. And the other thing we might want to do, as we notice here, is they get smaller as they're branched off. So let's also, when we're creating this child branch, let's also, and let's make sure we hit stop, let's also set a local scale. And we can just always make it half size. Vector 3, 0.5, 0.5, 0.5. So it's always going to be half the size of its parent, because it's always this scale, since it's a local scale, it's always relative to its parent node, so its parent branch. So it's going to be, if the parent branch is scaled 50%, then this is going to be 50% of the parent branch, which will be 50%. So it'll be a quarter of that, and so it's going to keep making its way down from the parent branch, a quarter of the parent branch, or the root branch. So let's see what happens now. So now we start getting this kind of interesting effect where they keep getting smaller, and we get that kind of like bristly kind of tentacly effect here. So we just keep hitting play, and we see all these different variants here. One thing we might want to do, I think, is we might want to make these a little bit longer. I think the distance is too short for these child ones. Let's crank up the distance here. So we were choosing a random from 5 to 25. Let's go from 10 to 60 instead. Ooh, so that's a much more like complex lightning bolt here, but it looks much nicer, I think. Crank up the speed here of the camera. So that's nice. That's starting to look kind of like lightning bolty. I'm gonna make these a little bit bigger, maybe the radius. Crank up the size of the radius a little bit bigger. There we go. Maybe that's a little bit nicer. We don't have to go 50%. Maybe we go 75% each time, so that it maintains a little bit more size. It might look a little bit nicer. Sort of. Yeah, I don't know. From the pictures, I really feel like it's 50%. Like, if you look at all the pictures, it almost looks like it is 50%. That's why I feel like 50% looks nicer. Let's stick with 50%. So one thing you got to be aware of is if we make live changes to the script, what's basically happening, this is an important thing to be aware of, it's every single time it updates the script, it's going to recall on init. And so that's why as I'm making changes, it's like adding more and more bolts to the space. It's because on init is actually getting called. When Simmetri detects a change in the script, at playtime, it will recall this script. It'll reinitialize the script, which calls on init again. So we have to be careful if we have any initialization code, is that'll keep getting called every single time we make live changes. Okay, the next thing we're going to do before we proceed here is I'm going to just comment this up a little bit here. So we're going to create a blank. Always make sure you comment your code. Super important. You should have one line of comment per every line of code. I don't always do that in these tutorials, but it's definitely important. So we're going to create a blank node to contain our branch. And then when we have a parent, we'll adjust it to place it on it and add some root rotation and scale. And this is our loop, or repeat until our length is reached. And this is like position from last segment. Choose random length for segment. Choose random rotation for segment. And recurse down through child branches. Okay, so that's good. So let's keep taking a look here and see what we get. So that looks really nice. One other thing we might want to do is fade out the tributaries a little bit. You'll notice they tend to have a less opacity. So to do that, what we can just do is we can use this depth value and set the opacity of each of them to kind of reduce it down a little bit. So what I'm going to actually do is I'm going to go in here and I'm going to set the I'm going to detach its color, because we're going to want to set each, since these are shared copies, we want to make sure that each of the copies has its own color value, because what we're going to be doing is we're going to be setting an alpha value per copy, per value, per segment. And then the other thing we need to do is in the materials, if you go into translucency, you're going to want to say use the diffuse map alpha. If you set this to true, it will now use the diffuse value, the alpha channel of the diffuse channel, and which in this case will come from the color. So we're going to be able to set now the opacity individually per object by setting this value here. So now let's calculate our opacity based on our depth. So we're going to say our alpha is equal to, and alpha is a value from 0 to 1. So if we set it equal to depth, so initially the depth is going to be 0, so we're going to say 1 minus the depth. So initially you can imagine for the trunk, depth is 0, so the alpha is going to be fully opaque. The next one, it's going to be 1 in the depth, which means it will go to completely opaque. So since we have 3 depth levels, we can just divide our depth into 3 segments here. Divide that by 3. So as depth goes to 1, it's going to be 1/3, 1 minus 1/3, 0.66, and then 0.33, and then it'll go to 0 for the last step. So now we're going to set our line segments color is equal to, and what we're going to do is we're going to pull it out first. We're going to say our color, I'm going to do this locally, our color is equal to line.color. Now we're going to go and set the W channel, or the alpha channel in this case, is equal to alpha, and then we're going to set it equal to that. And it's a little bit harder to see, but they are less opaque. The problem is it's so bright that the opacity is only noticeable right at the end of the alpha channel. So if you'll see it's still opaque, and it's just toward the end that so that's why maybe what we have to do is modify this material a little bit. I'm going to set this to be additive instead of alpha blended. That gives us a lot more kind of variability on the alpha channel. And then maybe we'll make it a little less self-illuminating. That'll give us a little bit more resolution. So I'm going to go in here and set the self-illumination to maybe 0.60. So, it's okay, good, not great. Opacity is still a little high. You'll see what happens if I set the self-illumination to 1, for instance. Very dark, but now the opacity will be a lot better. It's just when we start to exaggerate that brightness, we essentially we want to affect the alpha channel a little bit with a different scale, basically. Let's see here. Let's go into the Lightning Manager. And actually, since we're dealing with an additive now, we can actually just multiply our color. We don't need to set that. We can just say it's just times the alpha. Maybe we can square the alpha, see what that looks like. That looks better, maybe. It's a little bit too severe there. Kind of a formula we can kind of play around with. Let's just kind of leave it like this for now, times alpha, so we just you can kind of see it we have a lot more resolution on it. So it looks pretty good. So the other big thing now that we're going to have to look at is, cool, this is nice. Now the one thing you're not noticing is that when I hit play, well in this case you're seeing it, it's blocking basically because it's taking a bit to compute that initial, calculating all of this all at once in one frame means it can potentially block the more complicated our lightning is. And so what we really want to do is we want to make this something that we can just use in real time as a program is running, so that we can kind of invoke it randomly and have it kind of work that way. It'll be a lot better. So to do that, we're going to basically have to. There's a couple ways we can think about this. One way would be to pre-generate maybe like a dozen of these lightning bolts ahead of time, store all of them, and then kind of randomly choose them in the show as it proceeds. You kind of randomly choose them, and then that certainly is one way to do it. You could just essentially cache all of that. But I kind of like the idea of just always getting a random lightning bolt, no matter what, no matter just arbitrarily. I don't want to have to pre-cache 10 magic bolts that we always see repeated. Now the thing is, if we were to choose 10 random ones and rotate them kind of along the y-axis, it probably would be such that the user might not ever notice that they're actually just a group of 10. But for the sake of this example, we're going to do it so that it will always be random, because I think it'll just look nicer. So how do we do this? Our main thing that we need to do here is we need to kind of move this function here, this thing that's blocking as it's building out this lightning bolt. We kind of have to do this across frames. We don't want to do it all in one frame. We want to do it across frames. So to do this, we're going to use a tick event. So we're going to say global script on tick. So this is the every object implements this. This is basically a function that will get called every frame. So if we can figure out a way to move this logic out of here and kind of separate it out into some sort of tick event, we can do this across a period of time, so it doesn't happen all instantaneously. And that actually is good because lightning generally doesn't happen all at once. It tends to have that kind of that effect where it's kind of percolating down the structure. And so we can kind of get that too. So we not only divide all of our work across frames, we also can use that as a way of visualizing the lightning kind of extruding through the space. So how do we do this? So the first thing I'm going to do is, it's always good just to keep our gold standard. I'm not going to modify this code here, so we can always refer back to it. So I'm just going to remark this, and I'm just going to copy and paste from here. So the first thing we're going to do is we're going to create our draw branch function. It's going to be the new draw branch function. It's going to instead occur across frames. And it's going to have the same exact parameters. We're taking a parent branch, a position for that lightning bolt, a length for that lightning bolt, and a depth value. And every single time, I think the way we're going to think of this is we're going to create our branch. I think this is going to be, that's not expensive, so we can do that every time we call this draw branch function. We'll create our branch. We will position it with respect to the parent branch, etc., and keep that all the same. Now we've reached the part of our loop, and this is the bit that we want to try to pull out. So to do this, we're going to create a stack. So a stack is nothing more than just a table in which we're going to add objects onto this table, and these objects that we're going to be adding are going to store our state, our iteration state. And in this way, we can then work on it every frame a certain amount, exit out, and then on next tick we can kind of resume where we left off. So it's essentially basically making this loop here, changing it in such a way that we can call this loop in piecemeal across frames, but we will be able to kind of get back where we left off is the idea. So we'll store all the state of this loop inside this stack, in this stack object, so that we can kind of resume where we left off. So to do this, I'm just going to define a table. We'll do it up here. This is going to be our lightning stack, lightning stack, and it's just a blank table initially. And so what we're going to do in here is, so our table now, inside this table, this stack, we're going to, every element inside this table is going to store a descriptor, an object that's going to store the state of our loop, of our, wherever, what is the current v position or the end pass, or what is the current branch length that we've added up. We're going to store that inside this object. So I'm just going to call this our lightning context. I'll just call it our lightning, the current kind of our branch. What do we want to call it? Our branch state. How about that? That's good. Our branch state. State. Branch state. There we go. So every element of this table is going to store a branch state. So what do we need to store inside our branch state? Well, we're going to have to pass in our max length. We're going to need to know about that because that's inside our loop, and so we need to know when to exit out. So our max length is equal to our max length. We can store our depth as well, although in theory we could query that. Yeah, let's just store the depth inside there as well. Let's store other stuff we might need during the loop. We're going to need to store the end position and the current length of the branch, and this will all make sense in a second. Excuse me. Okay, so we're going to store our current length. I'm just going to take this branch length. That's going to be 0 initially, and we're going to store our current vNPass branch state vNPass. It's just going to equal 0, 0, 0 initially. Just like we initialize it to 0, 0, 0 here, we're literally just doing the same exact thing here. So now we have this variable that stores all of our, we probably want to store also our parent branch in there as well, or our current branch, sorry, this object here. We're going to need to add that, just like we need to access that inside of our loop as well. So literally what this is just doing is just storing all of the state that we normally use inside of our loop here. We're just storing it inside this object, of which we're then going to store inside this table. So our table lightning stack at the total number of elements inside that table, which initially is 0, plus 1, that's the index, is equal to this branch state. So this you do a lot. This is actually like a way of adding a new element to a table. You're basically saying, on this table, take the total number of elements in that table, which the table starts with 0, so this will be 0, add 1, because you want to set Lua is one index space. So Lua treats the first element as the number 1 in an array. So you want to make sure your first element is always 1, and then 2, and then 3. So then on next invocation of this function, if there's already an element in that stack, this will be 1, so then 1 plus 1 is 2, and so you're filling it 1, 2, you're setting the index of element 1, then you're setting the element of index 2 and 3, and so forth. So this is how we add new items to a table. So our table now stores our branch state. So if we were to call this again, let's say, if we call this twice this function, it would add first the state of it one time to this, and then if we call it again, which is going to happen when we call this recursively, it's then going to, again, add to the table the new state inside the top of that table. So in our tick function now, what we're basically going to do is we're going to always ask, we're going to basically say, give me the top item of the table, give me the last item that was added to the table, and given its state, we'll advance the lightning to some amount in that frame. And then so long as nobody adds any new items to the table on next frame, it will keep advancing it by pulling the state out of this branch, this table, until we've reached the end, at which point we're going to remove that item from the table, and then we know it'll be empty. So if our current lightning stack table is empty, don't do any work. So this tick function is going to get called every frame. We want to make sure if we haven't added, if nobody's called draw branch, i.e. this has not gotten filled if anything, we'll just kind of exit out is what this does. So on tick, it just won't do anything. If not, if we do have an element in the table, pull that element out. So our branch state is equal to, and we're going to take the last item added to our table, which is just going to equal to that, plus, equal to that, sorry, yeah. So if we have one item in there, we're going to take the last item from that table. And so we're always working with the last item added. So you can imagine in a recursive case here, as we're working our way down the trunk, and we add a child, as soon as we call draw branch recursively and we add that child, from now on tick is going to kind of work off that child first. This is kind of a depth first kind of way of thinking of it. It's going to operate on that child first, and then when it's done, it's going to remove that item from this table, and then it's going to continue on down that main trunk. We can think of it, and that's kind of what we want. The lightning usually kind of percolates out from wherever it comes from, initially. It doesn't go first the trunk and then the children come out. I mean, I don't know. Lightning obviously is very, unpredictable the way it kind of manifests, so I suppose maybe that's just a way to rationalize this way of doing it. But okay, so that pulls out our branch state, and now what we're going to do is we're going to just take this inner part of this loop here, and just going to do it inside here now. So we're going to do this once per frame now, and then we're going to make some adjustments so we do more per frame. So now we're going to, just like before, we're going to take our lightning segment, which we're going to take out of here. We're going to need to have access to that inside here. So we're going to make a copy of our lightning segment. We're going to set its parent node to the branch, which now is stored inside this branch state. So branch state.branch. We're then going to set its local position to, again, the branch state stores our current end position because we stored it here, which we initially set it to 0. Working our way down, we're going to choose a random length. We're going to set the local scale to that of that line. Working our way down and choose a random angle. That's all correct. Set the local rotation. The depth value, again, we're going to have to get that from our branch state. And we're going to proceed down and so forth. Our color is equal to that, and then we're going to recurse. Again, so we're going to calculate a new position here. So this is, again, going to come from that branch, that end position. Is equal to that times the length. That makes sense. And then we're going to recursively call this function. So again, that's going to call this draw branch function, which is then going to create a new node. And then it's going to queue up inside of our table, that branch state. So then on next tick, we're going to work on that child first before we get back to the parent. So that makes sense. We're going to pass in again our branch state branch for that. Branch position is correctly computed there. That's all correct. And then we're going to make sure we store that inside our branch state instead, and then we're going to update our branch length is equal to the branch length plus our length. So now we're just updating that state inside of our lightning stack. We're updating this object that we stuck inside there. We're accounting everything correctly. We're updating the depth value, or the depth, we're updating the branch length, the end position, and this branch value, and we're kind of accounting for all that. So the other thing our loop does is that it knows when to exit. There's this until statement. So now we have to kind of build that in here. So just like we were saying until, we're going to say until our current branch state branch length is greater than our branch state maximum, what do we call it? Max length. If it is, then we need to exit out. And to exit out is nothing more than we need to remove that item from the stack. We're done working on that item. that we added to the stack, so let's just remove it. So we're basically going to say that that item that's at the top of the stack is equal to nil. So that will essentially remove it from the stack, and because this is a simple array and we're adding them in a very simple fashion, in Lua, whenever you have a simple array, i.e. you add items using index 1, 2, 3, 4, 5, when you set that last index to nil, the top index to nil, Lua will return, it will act as if the table is shrunk by 1, and so this will shrink the table by 1. So if then tick gets called and our table is empty, from now on it won't do anything, any more work. So I think that makes sense. I think we have everything we need. Let's remark the recursion for now. I always like to kind of start simple just to make sure our root branch works here before we start adding complexity of the recursion. So again, we're going to call draw branch now. So when draw branch is called, we're going to call it with this stuff here, this nil, this position here of the initial depth 0. That's going to call this, which is going to queue up our job here inside of our branch state. It's going to create a node for it. Queue up the branch state, which is then going to go and it's going to do this across a bunch of frames. So this is going to be frame rate dependent, depending on so our frame rate. So the more times on tick it's going to get called, the faster the lightning bolt is going to get created. And there we go. So now this is not blocking. Every time I hit play, no matter how, well, in this case it's just a root branch, which is pretty simple. But you'll see that it kind of extrudes out now over time. It doesn't just appear all at once. So now that we've done that, let's bring in our recursion to make sure that is okay. That has, and that's one other thing we got to do here for branch state dot depth. We got to get that out of the depth value of the branch state. So same with this here. Got to make sure we use the one that's stored inside that the branch state. Depth +1. Then that's going to create it inside here. The depth goes in here. It'll get stored inside there. That'll give us a way of exiting out. That looks pretty good to me. Let's see what happens. There it goes. And so it's not blocking now, and it's drawing it. It's a little slow, but it's drawing it. And we're seeing some unusual spaces here between the branches. Let's see what's going on there. Let's see. Copying that. Parent branch, set the parent node. Local rotation, we're setting the position to that. Branch position, length. I just want to move on just to kind of get to some of the other stuff that we can do here. Yeah, it's some silly bug there that I'm not seeing off the top of my head, but the important thing is that now it's happening across a series of frames. And one of the things that we can kind of do here is if we want to speed this up, right now we're doing one thing per tick, basically. We're performing one extrusion per tick. And so depending on what our frame rate is, it could be fast or slow. We want to kind of control this per time, basically. So we're going to do more per tick than once. So I'm going to repeat. I'm going to do all of this. So essentially what we're saying is repeat to do this some amount of times. So until, for now 1. So we're basically saying we're going to calculate now a number. So our num segs per tick, and that's going to equal to some value that we're going to calculate based on our time. So we're going to say get our self, get parent, get timeline, get the time elapsed from last tick. And then we're going to convert that to seconds. And then we can multiply that by some value. So it's basically saying how many times do we want to do this per frame. And until we've reached that number, and then we're going to have to store a value to store that. So I is equal to 0 initially, and then we're going to say I is equal to I plus 1. And then once I goes past this number, we'll exit out of here. So if I is greater than that, then we'll exit out of here. And then we also have to make sure that if this goes to 0, if we're done, we don't want to keep iterating because we're going to be done. So if this goes to 0, then we're going to break out of this loop. So it's going to keep going, keep drawing branches, keep drawing segments until we're either until we've reached the total number that we want to do per frame, so we don't do too much work per frame, or this value goes to 0. It means we have nothing left to do, so we'll exit out. So all we have to do is define how many segments we want to do per tick. So this is, maybe we'll do 10 per second. So now we have it, we can kind of control for that. So 100 times per second. This is a pretty complex one here. So let's do like 1,000 times a second. So the more we do, obviously, the more it might get stuck. And so now it's getting a little choppy. And so we might have to also reduce the complexity. Maybe we only do a depth of 2 here. And now it's much faster. It's much faster. Much faster. And so another thing we can do is we can fade in these lines just by saying copy. This is our line. Fade in. So now they'll fade in as they're created. So now they look a little bit more faded in. So now they look a little bit nicer. And the other thing we might want to do is instead of and we also might want to have it fade out after time. So in other words, after this whole thing is created, we'll want it to fade out basically. And so to do that, when we call draw branch with this being nil, this like root draw branch, in here we can do a fade out. So else if we don't pass in a parent branch, i.e. this is a root branch, we can just fade our branch out after some amount of time. This is the branch that we're adding all of our children to. We can say fade out and orphan. This is how long to wait before it fades out. Maybe 3/10 of a second, and then it'll fade it all out. So it's like now we have that kind of periodic kind of, and then it disappears. Another thing we might want to do is instead of calling this explicitly on a knit, why don't we call this randomly and then pick a random position in the sky instead of having it do it every frame. And so to do that, we're just going to move. I'm going to remark this on a knit code, and inside the library, I'm going to create a new pulse, and I'm going to create a new random pulse. And I'm going to knock down its average frequency a little bit, so it happens a little less frequent. And then on the random pulse, on pulse, so every single time this pulses randomly in this case, we're going to call that draw branch function that lives inside our Lightning manager. So I'm just going to drag and drop this in here, and I'm going to say draw branch. It's going to draw a root branch, so nil. And we just got to pass in a position in this case. So a position and a length. So our position might be, let's choose a random position outside this actually. So our v random sky pass is just equal to a random vector. We just say vector 3 math.random. We'll go from -10 to +10. So this is an area that revolves around maybe -40, +40. Our height, we'll choose a random value that goes from, I don't know, 50 to 80. That's up in the sky. And then again, along the z-axis, let's just choose a random value that goes from -40 to 40. So that'll be a random sky position, so null that. We're going to need a random length, and that's just going to be the y value of whatever that random sky position is. So it should always go about to the ground, and then 0 for our initial depth. So now whenever this randomly strikes, we should get a random pulse here. And that's still really bothering me, that bug there. I just don't want to waste everybody's time trying to fix it here. But I will fix it and then post up the result. It's something really dumb, I'm sure it is. I just don't... It's tough to do these things live because it's like, ugh. Okay. So another cool thing that we can potentially do is, well, there's a couple of things that we might want to do to make a realistic lightning. One is the sound. We might want a nice thundery sound. And we can actually also calculate the speed of sound, and depending on where the viewer is, we could make it make a sound only depending on how far away you are from it. So let's go ahead and do that. So what we can do is, if I hit Control Alt and or actually find whatever Control Shift, sorry, open bracket, we can search free sound where we have lots of different sounds that we can choose from. I'm just going to hit thunder here, And I'm just going to choose this first one here. I think this from my test was pretty good. Hope you can hear this. Yeah, you should be able to hear this good. What we need to do is we need to edit this just a little bit so that we get it to be the exact moment of the thunder. In this way, we can, it's more accurate in terms of when we calculate the speed of sound, we're going to actually have it play the sound exactly at the moment of thunder. So I'm going to download this Rain and Thunder here. And this is by artist Flat Hill on Freesound. Download this. And then I have this other little website that I like to use called Audio Trimmer. And I'm just going to drag and drop that sound that we just downloaded onto this Audio Trimmer site and isolate out that sound of where the thunder starts. That's pretty good. Let it trail off. And maybe we'll use a fade out here. Crop that, download that, and that'll be our thunder sound. So I'm going to import that into here. Which one was that? So I had another one. That was Flat Hill and Rain. Import audio clip, Flat Hill and Rain, Audio Trimmer. Okay, so we have our sound here. I'm just going to drag and drop this into the space. We add it to our space. And then what I'm going to do is I'm going to adjust this thing's inner radius. I'm going to make this really big so we can hear this, because we're going to instantiate this wherever the lightning actually happens, and then we'll have it play with some delay after we calculate the speed of sound, the distance with respect to the speed of sound. So we'll set the inner radius to nice and big. And finally, what we want to do is inside our lightning code here, we're going to go back to the train space, scripts, edit code. Inside here, I'm going to, when we call draw a branch, if we're drawing a root branch here, this is a good place to position the sound. We're just going to stick it wherever the location of the lightning is. So I'm going to just drag and drop this into here. This is our sound. Actually, I'm going to rename this to Thunder. I'm going to drag and drop this Thunder sound into here. We're going to position this first. So I'm going to set its world position to be our V position. And then I'm going to play a shared copy of it. Play a shared copy. And the reason why I want to play a shared copy is that if there's lots of lightning all at once, they'll kind of overlap each other. It won't reset the sound every single time. And we'll set that in copy. Oh, but we don't actually want to play it right away. So here's where we want to actually calculate the speed of sound and then play it a little bit into the future. So to calculate the speed of sound, let's go to Google and ask what the speed of sound is. Speed of sound. And it reports that the speed of sound is 343 meters per second. And that's perfect because our world space units are in meters. We consider one unit in world space. If I move a box from across by one, I consider that 1 meter because our scale in the space is calibrated around the scale is about 1 meter per unit of distance in terms of the scale of objects like the car and other objects like the train and stuff. That's kind of the assumed scale. So that's perfect. That's what we want. So let's calculate the amount of time we need to wait before we play that. So what we're going to do is we're going to take our location of our camera. This is our default camera here. I'm just going to drag and drop that in here. Just get its world position. I'm going to subtract that from the location of our thunder location. That's the top of the thunder where it comes out. That's close enough. We could use the XZ-axis and just do it in two-dimensional coordinates, but we'll do it using that. And our length. It's the distance to lightning. And we're just going to take that and divide that by 343, and that's going to give us our time in seconds. So our time to wait in seconds is equal to that. Because our distance is in meters, so we just divide out, and then we get the resultant seconds. And then we're just going to create a timer, create an animator, create a timer. And this is going to wait on ourself. We're going to call a function self.onThunder, and we're going to wait seconds time to wait in seconds. So it's going to call this function after that amount of time. And it's inside there we're going to call play shared copy. I'm going to define a function called on our global script called on thunder. And then we're going to pull in this object here. We're going to again we're going to get that thunder object here. We're going to make that copy here. We've already positioned it, so we don't need to. We can just make a copy. It'll get copied at its position, and then we're going to play the shared copy. So that should hopefully happen at that amount of time in the future. So let's see what happens. Oops. And so this is another thing that we find might happen sometimes. Because we're orphaning, we're removing, we're saying fade out and orphan here, which removes the whole thunder from the space when we do this branch fade out and orphan. After, if it's not done ticking over all of our lightning, then this will unfortunately the objects will all be removed. And so one way to kind of handle this is just to say, if this object goes away, if we don't have this anymore because it's been removed, so if either that or this thing is empty, it does not exist because it's been removed from that other statement, then we're going to return out. And actually we're also going to just clear out our table whenever that happens, so that we don't keep trying to access that table anymore. So if the object that we're currently processing has been removed from the space, we'll just go ahead and reset the table and clear it out. So you'll notice that this sound that we downloaded here has a thunder that's already been, you can imagine that this artist, Flat Hill, he recorded it some distance away from the lightning. And so a more complete solution to this is, if you know approximately the distance that the sound was recorded from, you could create a series of sounds where lightning was recorded at different distances, and then depending on your distance from the sound, from the lightning, you choose that sound, so that if you're really close, right now, even if we're really close, yes, we'll hear it right away, but it will be that kind of distant sounding thunder. So we would want to choose a series of different lightning sounds before, and then choose the one with respect to our distance from the lightning. So you'll notice right here, we're right near it, so we hear it right away. If we go really far away, look at that delay. Let me actually speed the camera far away here. There's some distance at which we won't hear it anymore, but yeah, we still have it. So it's pretty neat. Another little trick we can do here is if we go to our space and we set our fog value, and we set a non-zero density, and we create a light source, you'll see what happens when we create a light source when we have fog. We create a point light source. If we really exaggerate this light, it illuminates the fog. And so if we instantiate this light source briefly on the location of the lightning, we also will get the whole environment illuminated. So I'm actually going to turn off cast shadows on this just to make it a little less expensive. And we're going to deactivate this. And so now our goal is to also instantiate this when we create our lightning in our lightning manager. So back in the lightning manager, I'm going to, when we create the lightning here on this root branch, we're going to also stick our light source. For this one, we'll just stick it. We'll just use one. Say .active. We're going to fade it in, and we'll set its world position to equal the location of our lightning. And then we're going to fade it out. So then we're going to say fade out and deactivate. And we're going to wait a certain amount of time before doing that. So maybe 0.1 tenth of a second. Oops. So we keep getting this issue here, and again, this is because of this fade out and orphan thing here. So how can we address this problem? Why don't we, one way to do this is, instead of doing this like this, let's create a function, getAnimator. I'm going to create a timer that's going to call this after a certain amount of time. Oh, another thing actually we can do here is, if we try to draw a branch, and we currently have, this will prevent us from creating more root branches than we need to. So if our parent branch is nil, so we're trying to create that root branch, i.e. a random pulse is attempting to create those root branches. And we have jobs that we're still trying to finish. Let's not allow us to create more thunder than one at a time, basically. So if we currently have elements in our lightning stack, and our lightning stack is greater than 0, then we're just not going to do anything. So basically, if we try to create more root branches, it will wait until this thing goes empty before we're allowing more to come in. And so that might address this problem. So if we crank up the fog here, the density here, we start to get that kind of illumination effect. Still getting this thing here. So this object branch object should have not existed. Oh, right, we got to move this logic actually inside this loop, right? Because it's not existing as we loop back around. The next branch, it's gone. So let's stick it inside here. If not exists our branch, then we're just going to break out. And again, I think this is a good opportunity. That means somebody has removed us out of here. It's a good opportunity to set this to nil, just remove our lightning stack, our jobs. Because it means somebody has started removing us, which means we should just remove the whole thing out. So that should fix that problem. So another thing we can do is we can populate this space with something interesting here. I'm going to just go to Google Poly here and search for like a skyline. And this one was interesting, block skyline. I think this is Kuala Lumpur. Doesn't say, but looks like it has that kind of funky building that they have there. Let's say nothing about what this is. Okay, but this looks kind of neat. Download this, and I'm going to import this optimized. It's the model we brought in. It's a lot smaller, so I'm just going to scale this up here. So it's transform scale. Let's do like 400. No, let's do 100. Yeah, that should be. Yeah, 100 should be good. It might be way too big. Now let's do 10. Maybe we'll create a little terrain for this. Very, very frequent, so we can knock down the frequency of our pulse. And maybe we'll set this to be a little bit darker, this world here. We'll set the clouds. There we go. Increase the speed of the wind here. Let's get rid of this thing here too. This thing's kind of annoying. Hide this. So there we go. That's a lightning effect. If we pause this halfway, you can kind of see it. I can pause that. We can get a nice little view. And again, that will be fixed in a second. As soon as this thing goes off, I go off live. I'm going to look at this and find the solution and figure out what's going on in about 2 seconds. It's just on the spot thing's always tricky. And so I'll share this on Steam. And if you have any other questions, you can hit us up on Discord. And we're always happy to answer everything. So thanks for watching, and keep an eye out on the Discord in a second for the updated Steam show, and I'll catch you later. Thanks for watching.